So let's start to talk a little bit about what implicit differentiation is. How can we take kind of the derivative of both sides of an equation when it's not just y is equal to something, but when the x's and y's are together in more complicated ways in an equation. So let's take a look at this example here on the document camera. So over here is kind of a traditional problem. Y is equal to x squared. And we know that the derivative of y with respect to x is equal to 2x. What we're kind of doing, if you want to stop and think about it, is that here you can think that we're taking the derivative with respect to x of both sides of this equation. So the derivative of x squared with respect to x is 2x, and the derivative of y with respect to x is the symbol dy dx. All right, so let's look at a more complicated example, something that's not a function. So x squared plus y squared is equal to 25. We know that this is a circle, and circles aren't functions because there are two solutions for everywhere where there's any solutions at all, almost. So let's subtract x squared from both sides at least and separate it and see if that makes our life a little bit easier. So we have y squared is equal to 25 minus x squared. And now that we have this, let's imagine taking the derivative of both sides of the equation with respect to x. So the right-hand side of the equation is what we're used to, 25 minus x squared. What's the derivative of that with respect to x? Well, 25 is a constant, so that term goes away. And we use the power rule, so this becomes negative 2x. All right, on the right-hand side of the equation, we're taking the derivative of y squared with respect to x. And in some sense, this is an example of the chain rule because we've got our inside function, which is y, which is in some sense a function of x, and our outside function is squaring the output. So whatever we get from this function, we want to square it. So to find the derivative of y squared with respect to x, we're going to use the chain rule. So the derivative of y squared is 2y, and then we have to multiply that times the derivative of the inside function, which is, like we saw, the derivative of y with respect to x. Okay? If you want to think about this in a more practical way, like I just want to do implicit differentiation, I don't need to understand it. Here's a place where where everything was just in terms of x. X was the dependent function, and it's just the normal thing. If y is the variable we're dealing with, then we just differentiate it normally and then multiply whatever we get by this term of dy dx. If that's how you want to think about it, that's absolutely fine. And then to find dy dx, we just need to solve this equation for dy dx. So we get that by dividing both sides by 2y, and we get negative 2x over 2y. The negative 2's cancel out, and so that becomes negative x over y. This is a little weird in that both x and y are in the function, but that's not completely surprising because this is a circle. If I had a circle and I wanted to know the derivative, the slope of the function at this point, I would need to know both the x value and the y value, because if all I knew was the x value, you wouldn't know which one of those 2 points I wanted to find the tangent at. So you need to know both the x value and the y value in order to find that derivative. So that gives you a little bit of a sense of how to use implicit differentiation to solve curves and find the slopes at a point. This was a fairly simple example. In the next video, we're going to do a slightly tougher example that's going to make us kind of leap out a little bit and need to use some of the other rules we've used up to this point.